Hello and welcome. So today we're going to finish up chapter 9. We're going to be working on normal approximation to binomial distribution. So in chapter 8, we talked about binomial distribution, calculating probabilities. And remember, to have a binomial distribution, you have to have a set number of trials, and the outcome, there are only two possibilities. That's it. And we usually label those as success or failure depending on the situation. So remember, in a binomial distribution, to find the probability of a certain outcome, we use the formula of the combination of n pick x times the probability to the x powered times 1 minus the probability to the n minus x powered. Okay. So that helps us with the probability. But with the binomial distribution, just like any other distribution, it would also be helpful for us to have the mean and the standard deviation. Well, earlier in this chapter, when we talked about expected values for binomial distributions, we determined that the expected value of x for a binomial distribution was the number of trials times the probability of success. And we also referred to this as mu, as the mean. So from that, we can say then that to calculate the mean of a binomial distribution, we use the formula mu equals n times p. And remember that n is equal to the number of trials, and p equals the probability of success. Okay, great. So from the mean, then we could calculate standard deviation. So we could calculate sigma. So standard deviation, sigma, is equal to the square root of the mean times 1 minus p. That's all we would do here. So where does that come into play? Well, the most basic of a binomial distribution is flipping a coin. So let's say that we flip a fair coin 15 times. And they'll say, find the mean and standard deviation, which I'm going to abbreviate, for the number of heads. Okay. Well, in order to do that, we need to know two things. We need to know the number of trials, and we need to know the probability of success. So in the example, they tell us the number of times. That's 15. So in this case, we're going to use n equals 15. And we know that the probability of flipping heads with a coin, with a fair coin, is 0.5. So using that information, now we can calculate sigma, or not sigma, we can calculate mu. We're going to do sigma here in a minute. So we know that mu is equal to n times p. So here we do 15 times 0.15, or 0.5, getting confused. So we get mu is equal to 7.5. Okay? Now we calculate sigma. So sigma is the square root of n times p times 1 minus p. So it'd be 15 times 0.5 times 1 minus 0.5. So this ends up being 15, the square root of 15 times 0.5 times 0.5. So it'd be the square root of 3.75, which is approximately 1.94. So from this, we can get that mu would be 7.5 as the average, or the mean given this situation, and that sigma is equal to 1.94. Okay, so now based on this, they could ask us to find the probability of flipping 9 heads. Okay, so to find the probability of flipping 9 heads, we use the formula from up here. So if I want to find the probability of 9 heads, we do the combination of 15, choose 9, times the probability of flipping heads to the 9th power, times 1 minus the probability of flipping heads to the 15 minus 9 power. So that'd be the combination of 15 choose 9 times 0.5 to the 9th power times 0.5 to the 6th power. So when we do that calculation, when we punch that into our calculator, we get 0.1527. So the probability of flipping heads 9 times in this given situation would be 0.1527. Okay. Now, here's the interesting thing. As we start to graph this probability distribution for this given situation, we create the histogram. The one thing you'll notice about the histogram is that the curve of the histogram starts to become more and more normal. And that occurs when you have a large value of n. And in this case, 15 is considered large. Anything above 5 is considered large. So again, as we start to graph this, we notice that the curve becomes larger and larger and larger. So based on this, we have another way that we can find the probability. And that's by using what's called normal approximation for binomial distribution. So in a normal approximation for binomial distribution, what we're going to do is we're going to find z-scores for a little bit before 9 and a little bit after 9. And then we're going to subtract those two to find the area in between. So in this given situation, what we would do is we would find the area between 8.5 and 9.5. So in this case, we would do a z-score for 8.5 using mu and sigma. So we would do 8.5 minus 7.5 divided by 1.94. That would be 1 divided by 1.94, which gives us a z-score of 0.52, approximately 0.52. Then we would do the same thing for 9.5. So we would do 9.5 minus 7.5 divided by 1.94. So that's 2 divided by 1.94. 2 divided by 1.94, which gives us an approximate z-score of 1.03. So when I go to the table on page 814 for the positive z-scores, a z-score of 0.52 would be 0.6985, and a z-score of 1.03 would be 0.8485. So then what happens is, if I subtract these two, 0.8485 minus 0.6985. When I subtract these two, we end up with 0.1500. That's really close. So we calculated using the binomial probability formula to get 0.1527, but if I wanted to approximate it normally, I could, and we get a pretty close approximation, 0.1500. That's almost there. So again, we can use this idea of normal approximation when given a binomial distribution. Okay. So, one more example real quick. So, in another example, let's say that we did a random sample of 100 drivers in Michigan City. And 40% of the drivers go 10 miles an hour over the speed limit. Okay? So here they could say use the normal distribution to approximate the probability of at least 50 drivers. So at least means x is greater than or equal to 50 will go 10 miles an hour over the speed limit. Okay. So, well, in order to make this happen, we need to know two things. We need to know sigma and we need to know mu. So in this case, we know that our n is 100. That's the number of trials from our sample. And we know that our probability is 0.4. We have a 0.4 probability of choosing, a 40% chance of selecting a driver that goes 10 miles an hour over the speed limit. Okay. So we calculate mu. So mu is equal to 100 times 0.4, which is 40. And we know that sigma is equal to the square root. Well, it's going to be 40 times 1 minus 0.4. So that'd be 40 times 0.6. That'd be the square root of 24, which is approximately equal to 4.90. Okay? So now, what we can do with this is, now that we know this, now we can use normal approximation. So I can do a z-score. So we do x minus mu divided by sigma. So our x is greater than 50, so I'm going to use 50. Or actually, in this case, back up. So instead of using 50, because I made a simple mistake that many people will make, because it is a normal approximation, we want to use x equals 49.5. So it'd be 49.5 minus 40 divided by 4.90. That would be 8.5, and I'm just going to make it 4.9. So 8.5 divided by 4.9 gives us a z-score of 1.73. Okay. Now, pay attention to the inequality. because it's greater than, if I look at the curve of this situation, we know our mu is 40. We know our standard deviation is approximately 4.9. Because we're using an x value of 49.5, and I want to know everything greater, remember that for normal, the area under the curve represents the left. So in this case, to do anything to the right, we have to do 1 minus the probability that would represent this area. So when I go to look up a z-score of 1.73, we end up with 0.9582. So this translates to 0.9582. So to find the probability that x is greater than or equal to 50, we would have to do 1 minus 0.9582, which gives us a value of 0.0418. So there's a 4.18% chance of selecting 50 drivers, of selecting more than 50 drivers that will go more than 10 miles an hour. Okay. So now, the next example, this time they want you to do the probability that x would be between 42 and 48. For a random sample of 100 drivers. Okay. So again, this time, because it's 42 and 48, we're going to use the normal approximation. I want to pick x is equal to 41.5, and I want to pick that x is equal to 48.5. So I'm going to do a z-score for both of those. So if I do the z-score for 41.5, it would be 41.5 minus 40 divided by 4.90. So it'd be 1.5 divided by 4.9, which gives us a z-score of 1.5 divided by 4.9. So that's 0.31. And if I use 48.5, 40 divided by 4.9, so that would be 7.5 divided by 4.9. So that gives us a z-score of 1.53. Okay. So when I go to look these up, the 0.31 probability is 0.9531, and the 1.53 probability, no, not 91, it's 91, not 31, so 0.9591, and then the 1.53 probability is 0.6217. Okay, so now to find the probability that anything would fall between 42 and 48, we would subtract the 0.9591 and the 0.6217, and that gives us a probability of 0.3374. So approximately 33.74% of drivers has the probability of selecting between 42 and 48 speeders. All right, great. So if you have any questions for me, please feel free to reach out, send me an email, or send me an email and ask me to do a Google Meet. Your assignments are posted on my math lab, and we'll talk to you later. Have a great day.